Welcome back, class. So, this is the lecture number 10, and in this lecture, we will discuss about the nucleophilic aromatic substitution reaction and their mechanism. Okay, as we are discussing the chemical properties of haloarenes, in that particular context, this is the lecture number 10. So, today's discussion is based on the nucleophilic aromatic substitution. Aromatic substitution. A nucleophilic aromatic substitution. See, as in the ninth lecture, we have a question. We have a question that the chlorine is an electron withdrawing group, yet it is ortho and para directing in its electrophilic aromatic substitution. Point to be noted, that was electrophilic aromatic substitution. Here we are talking about the nucleophilic aromatic substitution. Okay, so we know that the aryl halides are showing their less reactivity towards nucleophiles. Okay, because of the reason which I have explained. There are several reasons for that. So the aryl halides aryl halides less reactive are less reactive towards nucleophiles. Nucleophiles, what are the nucleophiles? Like OH, then RO, CN. Okay, these are some nucleophiles. So aryl halide shows less reactivity, but in presence of electron withdrawing group, but in presence of electron withdrawing group at certain position, that is very important, at certain position, and that position is what? Ortho and para. We will discuss it why it is. Okay, at a certain position, ortho and para, certain position in the ring, enhance the reactivity, enhance the reactivity. So this is very important. In presence of electron withdrawing group at a certain position, the reactivity is certainly increased. So let's take some examples. Well, the example number first, if you have chlorobenzene, okay, only chlorobenzene you have, and if you want for the nucleophilic substitution, so let's take an example of NOH. OH will be nucleophile here, and you want to substitute this OH with the Cl. So without electron withdrawing group, the reaction is very difficult. The condition you required is temperature and pressure. So 350 degrees Celsius temperature, and something like 4000 to 5000 atmospheric, not, it's not atmospheric, if you just convert this value into atmospheric, so it required certain temperature pressure also. So this will give you phenol. What I'm trying to tell you that if there is no electron withdrawing group is present, then you required some pressure and temperature. Okay, now what is effect of electron withdrawing group? So let's go for the second example. In second case, if we have electron withdrawing group NO2, okay, this is chlorobenzene, and if we have an electron withdrawing group, so this is para nitrochlorobenzene, and in that case the nucleophilic substitution will occur with only 160 degrees Celsius temperature. Just point to be noted is that here the temperature was 350. So as you put one electron withdrawing group at para, the condition is change, and you will get the phenol substituent here. So this is called para nitrophenol. Okay, this is para nitrochlorobenzene, and this is para nitrophenol. Now just go for another example, the third. Now if we have a chlorobenzene, and then in this case we have two NO2 group, one is at ortho and other one is at para. Now what will happen with the condition now? So again we have you can take here aqueous Na2CO3 only. This will also help you to withdraw this Cl. Okay, and temperature is 150 degrees. As you can see that as we are adding the electron withdrawing group, these all are what? These all are EWG, electron withdrawing group. This is electron withdrawing group, this is electron withdrawing group. So this will help to reduce the temperature and other reaction condition. So here only at 150 degrees Celsius you will get the desired phenol substituent. Okay, so this is the phenol, and NO2 at no harm, no change occur at the ortho and para position. We'll take one more example. So in this case we have chlorobenzene, and in this case we have three substituent NO2, NO2 and NO2. So this is called 2,4,6 trinitrochlorobenzene. This is 2,4,6 trinitrochlorobenzene. Now if in this case we have three electron withdrawing group. Okay, so now here we have one EWG, here we have two EWG, and here we have three EWG, electron withdrawing group. So in this case just presence of water and heating, this will give a desired product. This will give you phenol derivative. That means the OH and NO2, NO2 and NO2. And the name of this compound, very famous name, you all know that. Okay, this is called 2,4,6 trinitrophenol. This is trinitrophenol, and one more name is there, and that is nothing but picric acid, acidic of nature, picric acid. Okay, so just rewind all these reactions. See, chlorobenzene is less reactive, so it required certain temperature and pressure, then only it will convert it into phenol. But as electron withdrawing group at a certain position like ortho and para, it will certainly reduce the temperature and pressure. Okay, so here we have 350, in this case only 160. Similarly, next only 150 degrees Celsius, and at the end, when we have a 3 electron withdrawing group uh, at ortho and para position, only normal heating can done the same thing. So this is what the importance of the electron withdrawing group here, and that is why I'm saying that the role of electron withdrawing group is very important. Okay, this is one thing. uh, Now if we have you can go for other examples also, like you can take one more example. Let's take some more examples so it will clear you. If you have question 5, so if you have a chlorobenzene, okay, chlorobenzene, and then if we want to replace it with amide, okay, so this is the NH3. So again I'm repeating, chlorobenzene is less reactive, so it required certain temperature and pressure, 200 degrees Celsius temperature, 1000 pressure, and it required some catalyst also, that is Cu2. So this will give you what? This will give you amide NH2, that is called, that is nothing but aniline. Okay, but the same reaction will happen with different conditions. See, if we have a chlorobenzene, okay, containing NO2 and NO2, 3 nitro group, okay, same NH3, only 20 degrees Celsius, nothing, and you will get desire. So this will give you NH2, NO2, NO2, and NO2. So this is what difference the difference create when we have a electron withdrawing group. Now it is very important to understand the mechanism, what mechanism it follows. Okay, so let's talk about the mechanism. So this is the page number 1, and we have page number 2. So let's talk about the mechanism here. What is the mechanism? What happened actually at ortho and para position? See, it's all about the resonance stabilization. Okay, it's all about the resonance stabilization. What happened here, if we have a chlorobenzene only, okay, this is the chlorobenzene, and this chlorobenzene actually you can draw it by any mean. Okay, there is no harm to draw it with different pattern. And then we have a nucleophile. Okay, so OH negative, this is a negative charge. Now what will happen, this will certainly attack to this. Okay, and this is a slow step, and we get Cl OH, and if you can change, this is the negative charge, because if you draw in this pattern like this, okay, So this will attack to this side and this will go to this side. Okay, so this is why. This is resonance stabilized because this is a carboanion. Actually this is a carboanion, so it will be resonance stabilized. Okay, so we can draw the resonance structure of this. So let's go for the resonating structure. If you go for this, what will happen, this will come to this side and this pi electron will shift to this one. So this will give you a negative charge here and this Cl and OH, and again hydrogen here. Then this electron will shift to this side, this will go to this side, and so this will give you a structure like this. This is a negative charge with hydrogen, and here we have a bond, OH and Cl. So finally we will have a resonating structure in the carbon and ion, negative charge Cl and OH. So how many resonating structures we have? First, second and third in case of chlorobenzene. Now what effect of NO2? This is a normal chlorobenzene. Okay, then what effect of NO2? So NO2 at para position. First we will take the para position. So what effect of NO2? Point to be noted here, in case of chlorobenzene we have only 3 resonating structure, and we know that as the number of resonating structure increases, the stability of the intermediate is increases. Okay, so the higher the resonating structure is always preferable. So let's take an example at nitro para position. So this is your para nitrochlorobenzene NO2, and I'm drawing the NO2 in this pattern, and double bond O and O negative. Okay, so this is a positive charge, and then we have a OH negative. So this is a slow step. This pi electron will be, so this will attack here and this will go to this side. So what we'll get, we will get a negative charge here and Cl OH and then and double bond O negative with a plus charge. Okay, this will be resonance stabilized. So this negative charge will goes to this side and this will move to this. So the next will be a pi electron here, pi electron is here, Cl OH, and here what we'll get, see this will be electron. Okay, so here we have a possibility to shift this electron pair to this side also. Okay, because once it will shift to this side, what will happen, this pi electron, so it will be resonance resistor, this will go to this and this will go to this, and then what we'll get a double bond here with nitrogen and oxygen with a charge of negative, and this oxygen. You can draw a coordination bond also here, so that will be easier for you. Okay, if you draw a coordination bond, so this will give a clear idea. Let's draw a coordination bond here, so don't be get confused. Okay, and then this is a positive charge. Now what happened with the next stage? In the next stage, again this will shift to this side, and this pi electron will shift to this side, and this will go to this side. Okay, so what will happen here, this will give you Cl OH, and nitrogen with a double bond oxygen, coordination bond oxygen, and this is already shift to this side, so here we have a bond, pi bond, and here we have pi bond, and this pi bond will be converted to, so here we have a negative charge. Okay, and in the next stage this will go to this side, and again, so this is the process which will continue. So as you can see that the first step and the second stage, okay, then the third stage, and then we can go for one more step, and that is what, if you move to this electron to here. Okay, so I think there is something which we have missed, so let it draw again. I'm drawing it again, and this is the initial compound. We have Cl and N double bond O, oxygen with a positive charge, and here is the nitrogen with positive charge. Okay, and then the OH nucleophile, so this nucleophile will attack to this side. Okay, and this will move to this side. Now I am writing the resonating structure. Okay, so what will happen here, nitrogen with oxygen and oxygen positive charge, and here a negative charge will generate, and here Cl and OH. Then in the next step what will happen, this will move to this side, and this will goes to this side. Okay, so this is the second stage. Cl OH, this is the pi, this is the pi electron, and here is the negative charge. Okay, here is the negative charge, and nitrogen double bond oxygen and oxygen with a positive. So this negative charge will, now the resonance is stabilized with this NO2, so it will shift to this side, and this will go to this side. So in the next stage what we'll get, we will get double bond nitrogen oxygen negative charge oxygen, this is a positive charge, and then the electron. Okay, Cl and OH. And in the next stage, what will happen? This will move to this side, this will go to here, and this will move to this side. So this one I will have missed, no? Here nitrogen again in single charge, this will in double bond, and oxygen, this is a positive charge, Cl OH, and this is the negative charge. So as you can see that as the presence of a nano2 group at para position will certainly give you four structure: first, second, third, and fourth structure. Okay, what does it means? It means that this is wrong structure one. Okay, so this just leave it. So as you can see that in case of chlorobenzene only we have a three intermediate radionic structure. Okay, these are the three structure, first, second, and third. But in case of para nitrochlorobenzene we have a three, instead of three we have four resonating structure. And as we have a four resonating structure, so it will enhance the reactivity, enhance the reactivity, and higher the resonating structure, higher will be the stability. That is why we use here this term, that is the presence of NO2 group is always enhance the reactivity of chlorobenzene. Okay, now what similarly you can go for the ortho position also. If you draw the structure for ortho position you will get the same result. Okay, so I think is there a need to draw the ortho position, because it will give you same. That means one additional resonating structure will you'll get. Okay, but let's talk about the meta position. If it is at meta position, because we are talking about only ortho and para position. So if NO2 is at meta position, then what will happen? Because at meta position, if the number of resonating structure is equal to 4, then there is no need to discuss this rule. And if it is 3, then why it is 3 only. Okay, so let's talk about at meta position. So this is the structure of meta chloro meta nitrochlorobenzene. Okay, and then we have a nucleophile. So again the same thing will happen. This nucleophile will attach to this will move to this side, and now I'm drawing the resonating structure. So here the first structure is what at meta position. So we have a nitrogen plus O double bond oxygen, and here we have a negative charge Cl and OH is there, and this will give you the structure like this. Okay, then move for the next one. This pi electron will shift here, and this pi electron will go to this side, and now it will not resonate this NO2, because here we have single bond. This single bond cannot be shifted to this side. Okay, so what we'll get the structure like this. This is the electron, and here is the negative charge, and then here is a pi electron OH Cl, and of course NO2. Okay, so this is what the difference. Here you can see that this NO2 is a resonance, this creating a resonance structure, and that is why we have additionally one more resonance structure. But in this case there is no possibility to increase the resonance because this electron will shift to this side, so it cannot be go to beyond to this one. Okay, so that is what the reason we'll get the similar structure less like in chlorobenzene, only three resonance structure. So now I think you can understand that what is the reason that the ortho and para position enhance the reactivity of what chlorobenzene. Okay, ortho and para position enhance the reactivity of chlorobenzene. This is, in this case only we have three structure, first, second and third. So no difference between chlorobenzene and meta, or no difference between the resonance structure of chlorobenzene and meta nitrochlorobenzene. Okay, so this is, I think, all about with the mechanism part, that what mechanism it follows in order to understand the uh, reactivity pattern of chlorobenzene. So we will end this session with a simple question. Just complete this reaction. I'm writing in the very in bottom line. Okay, so just need to complete this reaction is that we have NO2 here, and we have NO2 here, and we have Cl here. Okay, and then we have C2H5ONA, and in presence of ethanol, just heating, what is the result? Only simple reaction. I think you can do it very easily. Thank you so much.